Chemical Kinetics Lecture Part 3. In this lecture, we will be covering integrated rate laws. Integrated rate law and the rate law just we discuss in the part 2 is not same. Rate law tells us how the speed of reaction varies with the concentration of reactants, where the concentration expressed as a exponent molarity. And integrated rate law express how the concentration changes over the time. Since we use the calculus for calculating this rate law, the change of concentration over time, that's why this rate law is also called the integrated rate law. So, summation or integrating the instantaneous rates of a reaction from the start of the reaction until some specified time, we can obtain the integrated rate laws that quantitatively give the concentration as a function of time. So, this is the actually equation. If we look into the equation, we can see the final concentration or the concentration at any specified time compared to the beginning concentration of F equal to concentration of 0 initial E exponent minus KT. So A0 is the initial concentration of reactants A at time 0 and AT is the concentration of A at specified time after the start of a reaction. K constant, we know that. So the rate, the change of concentration per change of time with respect to reactants A. And obviously if this is reactant are using and disappearing, so it's the negative equal to K A. Just a minute, I need to see whether the integrated rate law equation, I want to just make sure one time. Yes, so now we will move to the math problem. So we have the equation of integrated rate law. Now let's see the problem. So there is a reaction that dinitrogen pentoxide is not actually stable too much in the gas phase or dissolved in a non-aqueous solvent such as carbon tetrachloride. It decomposes by a first order reaction into dinitro tetroxide plus molecular oxygen. So this is our experimental condition and this is the reaction, and we are talking that we also know the information that this is the first order kinetics. Now at 45 degrees Celsius, the rate constant for the reaction in carbon tetrachloride, we are using carbon tetrachloride as a solvent, is 6.22 times 10 exponent 4 per second. So that means we already have K value. We also have the initial concentration of N2O5. If the initial concentration of N2O5 in a carbon tetrachloride solution is 0.5, what will its concentration be after exactly 1 hour? So we need to calculate the T. We have K and we have the concentration of the concentration of nitrogen pentoxide with respect to nitrogen pentoxide. at time 0. So what then after specified time after 1 hour? Let's see. So when we will convert the hour to second, you can see here we can easily convert and put the value. We will find the answer. So wait a minute, nitrogen pentoxide, yeah, 0.5 molar. Okay, so let's put the value. I forget to write the answer here, so let's do together. So the concentration of yes, so if we write from here after this line, oh, we already put here. Okay, we put the concentration. So let's take from this line and write here. So we will have the concentration of N2 O5, sorry, oops, time T point 5 molar, the initial concentration, and the E value we have the, if we put the minus, this K value and the T value, then I will get the final minus 2.39. You guys can do this calculation and also look into the book, the page number 645. Yeah, 2.2, sorry, 2.239, sorry, 2.239. So ultimately the answer will be okay. So this will be the concentration okay, and the value will be 0.053. Sorry, the value will come 0.0537. So the concentration, yeah, so that's molar. So we can round it out also. So this is how we guys can solve the problem using the integrated rate law equations, which is the change of concentration over the time. And I think this type of problem will come during your exam too. Another problem is here. If the reaction, so when designing a consumer product, okay, here I want to tell you something. When you buy any food, grocery, or even the food or medicine, we always see the expiry date. So actually the reason that how long the medicine's potential 100% efficacy or will be active. So normally we consider the 5% will be degrade, the not more than 5% in 2 years. So that means if any medicine we can use 2 years, it must have the 95% efficacy. So if we think like that, here we have one problem that often this means that active ingredient in the product should not decrease by more than 5%. As I said, 95% active product should be, or active drug should be remain in the medicine. It may be the tablet, solution, suspension. So now what rate constant must the decomposition reaction of the active ingredient have? So the change of concentration over time. The time is actually 2 years, correct? We can do per year, even we can change, but here I think we can do per year. It's okay. If you have a multiple choice question and you see that you don't have the year you need, but you have something month, then just you need to convert. Otherwise, it's fine. So A0 concentration of active ingredient or drug initially 100, but after 2 years it must be at least 95%. Should not decrease maximum. Should not decrease more than 5. So maximum 5% potential can be decreased, not more than that. So that means time t is 95. So if you put the value, we will have our answer. As I said, you see the this equation. We also have another ln. We can write the log or ln in this way. So if we put the ln, the concentration of time initial and final equal to k time, so we will also get the value. So here we will apply this equation. This is another form of the integrated rate law. If you want to know the detail, you can look into the books. Here is another reaction. Yeah, similar rule. So you can look into that. Now we will go see the relationship of rate constant for the first order reaction. As we know, the first order reaction, the rate is directly proportional to the concentration of reactant. So if we look into here, that the concentration is changing over time, see? So the concentration, if we start and look into, see the point here, 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 here. So from this viewpoint, we can find the slope and directly calculate the rate. And also if we have a value like the k time or the initial or specific time concentration, we can find from here, correct? And we can easily calculate. So if you see, this is the decomposition of nitrogen pentoxide, and as we said that in the first order reaction, the rate is directly proportional to the concentration of reactant, so over the time. So if we plot the change of concentration over the time, we will get the straight line when we plot the concentration versus time, and the slope of this line equals to the negative of the rate constant. Here we go, here we can find, and if we see here the slope, see the slope value will come negative. Half-life. Half-life of reactants means 50% is the amount of time required for half of the reactant to disappear. As we said that the integrated rate law is always the change of concentration over the time. So here half-life or T-half means what the time we need to disappear 50% of the reactants. So if we put the value time t time 0 half of, so we will find the equation for the first order T half equal to 0.693 divided by k. Actually this is ln 2 if we calculate it by putting the value, because here we take the ln, we can take the ln, even sometimes we can substitute the antilog to put the take your equation in the correct position what you need. So here we substituted if we substitute by T half, then we will have, and if we convert ln, then ultimately we will rearrange and find the value is here. T half equal to ln 2 divided by k, or ln 2 value is 0.693, so 0.693 divided by k. And also we can see that T half doesn't depend on the concentration, it just depends on the constant k, and obviously k is also related to molarity. Like here we go one k value, see, with the time, with time in case of first order, I think, in case of first order reaction, yes, here we go. So I skip the practice because if I want to tell each and every practice, the video will be going too long and it will be very boring for you guys to watch. So you guys, when you watch, you can see the practice how we doing. You can do the practice, and if you have a question, feel free to ask me. Now the radioactive decay of iodine. It also another application or example of T-hub using the first order law for integrated rate loss. And if we look into the concentration over time graph, so we can see here the beginning, the amount of radioactive iodine, and the first T-hub 8, and then 16, then 24, then 32. Here if we look into one thing, it doesn't depend on the how many particles. So if you see the concentration, the molecules too much, it takes 8 days. But when from this point to again we need the half of disappearing, we need another 8 days. If we notice this reaction, so what we can get from here? So half-life of first order reaction is not affected by initial concentration of the reactant. Just we find here, and you can see here. So if we do, then from this knowledge, if we do this math, so what we will see here? Suppose a patient is given a certain amount of iodine 131 as part of a diagnostic procedure for the thyroid disorder. Given the half-life of radioactive iodide, 131 is 8.02 days, what fraction of the initial iodine would be present in a patient after 25 days? If we look into the pattern, that every T-half is not too much affecting or changing on basis of the initial concentration. Whatever the concentration, but to decrease the disappear the 50% is taking the same time. So let's see what we have here. So we know that K equal to for the first order reaction, this is our equation. Also we have the equation ln A0 concentration divided by a T equal to Kt. So now we have the K value we can find from here because we already have T half 8 days. So that means we have K value. So now if we put the value, then we can use following equation to compute the fraction. Yeah, so if we value, so what we are getting, see, asking the what fraction of the initial iodine. So see here the fraction of the concentration of iodine. What fraction of the iodine would be present in a patient after 25 days if none of it are eliminated through the natural body process? It will be this fraction and the same. The reason that it's not this calculation is not affected on the initial concentration. So it doesn't matter it is eliminated from the body or not. So they will follow the same fashion. Here we have another math, please look into, and if you have a question you can ask me. Here, integrated rate loss second order reaction. In case of second order reaction, it depends on the concentration because the rate of second order reaction equal to K and square exponent power square to the concentration of reactants. So here our equation, change in concentration corresponding to time, and the half-life equation is this one. So 1 divided by K times initial concentration of reactants. This is a graphical representation of the second order reaction and the change of concentration over the time graph. And here the slope of this line is also negative of the rate constant. Here we have the decomposition reaction of hydrogen iodide which follow the second order reaction. So the problem, we have a reaction and we have K value and also we have concentration. So what is the half-life? So if we follow the if we put the equation, we can easily calculate the T half. The initial concentration we have 0.1 mole per liter, we have L K value and we need to substitute all the value here. We get the value we have K, see here, we have K here, we have the initial concentration here, so we will put the value and initial concentration and K value and we will get the result. And finally, for the zero order reaction, as you know, it doesn't depend on the concentration, and if we do the concentration of the reactant versus over the time, I mean plotted over the time or versus time, whatever we say, concentration of reactant versus time, so it will give us this equation. So actually we need to learn that the zero order reaction, first order reaction and second order reaction, actually how the relation with the concentration over time, and we need to know their equation, because then mostly the problem or question will come, you will able to sort out. Even if you don't have the value and if you got the graph, you can easily find the value from the graphical presentation and you can solve your problem using the equation. That's all here.